Today we're going to do a couple of applications. We're going to cover a series of sections rather quickly. You'll be happy to know that when it comes to testing, these are not going to be top dollar for any of the testing that we would be involved with. So let's first off begin with a very simple idea, and that is if you have a figure, it doesn't have to be centered at the origin or anything, there would be if there was a point in which it balanced both up and down, right and left. And the idea here is that you find an average of torque. And so torque is really a distance of how far away you're from an unknown point and then pushing down. And so we're really assuming that this is like a uniform massed object. If it wasn't uniform mass, then we can do it in a different way where we can use a density function. And the way this is found is we have a value x bar and y bar. Both of these formulas are quite similar. They are derived actually in the same way. But let's begin with the x bar, 1 over a. Then we have to do an integral, and the integral is quite simply going to be x times f of x and then dx. And this integral is going to take place over some specified region in which this exists. Now y bar is 1 over a, the integral from a to b, but its formula is 1/2 f of x squared dx. Now the derivations of these can be found on page 562. This one's a little bit more tricky because the y direction is not the same as the x direction. Now the application of these is simply given an object to find a balance point. Well, there should be a fairly simple example that we can do and confirm this. So let's do the most trivial example we can think of. Let's take the function y equals 1 minus x. And let's find out where this balances and then investigate if the y value takes on the same, y bar takes on the same as x bar. So first, x bar will be 1 over a. The integral, and this function exists from 0 to 1, of x times 1 minus x dx, which will be 1 over a, the integral from 0 to 1 of x minus x squared dx, 1 over a, x squared over 2 minus x cubed over 3, evaluated from 0 to 1. And 1/2 minus 1/3 is a sixth, and so we get 1 over 6a. Now a is obviously the area of this triangle, which is base height 1, height 1, so it would be area half. Why we're going to get the number 1/2. Kind of a surprise. I didn't expect to see that. All right, now let's take a look at y bar. 1 over a. Integral from 0 to 1, and this time it's 1/2 1 minus x squared dx, which will be 1 over 2a, and now I'm going to square this and integrate in my head. The x squared, when integrated, will be x cubed over 3. The minus 2x, when integrated, will be minus x squared, and the 1, when integrated, will be x, and this will be evaluated from 0 to 1. And get 1 over 2a, plug in 1, we get 1/3 minus 1 plus 1. That's a interesting, may have made a mistake. So 1/3 minus 1 is minus 2/3. So I get minus 1 over 3a. Something definitely wrong. So now we'll continue with this. We have 1 over 2a, x cubed over 3, minus x squared plus x, evaluated from 0 to 1. And when we put in 1, we get 1/3 minus 1 plus 1. We get again 1 over 6a, which is a half. Surprisingly, x bar equals y bar equals a half. All right. Now, our next section that we're going to have anything, by the way, we're not doing hydrostatic force. It's kind of a delicate subject that needs to be done on an engineering level, and it's just a formula that needs to be followed as well. And we have a lot of these we're looking at right now. So, biological examples that exist in a lot of different areas for our integration. Blood flow, cardiac output, ecological growth models. And in many of these cases, there's a very simple idea, and that is that we're describing something based upon a relationship. Might be a derivatives, for example, the growth of a population through time might be proportionate to the existing population, and this gives rise to the following. Solving for the exponential, we get e to the ln x equals e to the kt plus c, where we get x as a function of time is e to the kt and e to the c as a multiplier is some proportionality constant, a. And when you plug in 0, x of 0 will be e to the 0, which will be a, and so this is often called the initial population. This is an example of how integration differential equations are associated with physical problems. I recommend it. Take a look at the two things. One is the cardiac output on page 571 for those of you that might be going to the medical area, or on page 570 we have a blood flow equation. Most of these are very specific to applications in those traditional fields. Thanks for watching. Hope you're well. Chapter 8 is done.